Dr. Scott Rudy is a researcher at MIT Lincoln Laboratory. He graduated from Brigham Young University in 2016 with a PhD in computer science, focusing on security and HCI. Recently, he has been working on cryptographic enforcement of access control in Accumulo, which I believe you're about to learn all about. Dr. Scott Rudy.
Thanks. As you mentioned, I will be talking about how work we're doing at Lincoln Lab works to increase the security of Accumulo using different cryptographic tools. As you might have noticed, I only recently graduated, so most of this work is not things that I've been actively involved with, but it's a lot of the work that's been the team at MIT. So when we look at threats to Accumulo, we all know that Accumulo has an idea that we want security. We have visibility fields so that we can restrict who can access data. Obviously, that implies that there are threats that we are concerned about when using Accumulo. One potential area of threat is a malicious client. These clients can make unauthorized requests to the server. They can try to learn stored data that they shouldn't have access, or inject data that they shouldn't, that is malicious. Another area that we can have a threat is the network surrounding it and the different entities related to that. So for example, we can have external attackers that try to disrupt communication between the Accumulo server, try to inject malicious content at that point. And the third threat is actually at the Accumulo and Hadoop layer. We can have malicious server administrators who try to change the data that is stored in the database, try to read the data that's stored in the database that they might themselves not have access to. This is especially pertinent when we talk about moving the Accumulo data stores to the cloud. We all love the cloud infrastructure, but that comes with trusting somebody with all of your data, and maybe you're not so comfortable doing that. But you still want all the other benefits of being in the cloud, such as scalability and reliability. Our focus is specifically on this third area, looking what we can do to protect Accumulo against a potentially untrusted Accumulo server administrator. So we can look at what existing safeguards there already are in Accumulo. So if we talk about storing data at Hadoop, we can use data at rest encryption. Hadoop supports that, and we can encrypt the data while it sits stored on disk. Also, as that data is transported between the Accumulo instance and the client software, we can protect it using things such as TLS. But at the Accumulo level, in the presence of a malicious server administrator, there is nothing that Accumulo provides to actually protect that data. While the idea of things such as visibility expressions are meant to protect data, the administrator can choose to either give a user all the appropriate labels, or they could just choose to ignore them entirely. So the work we do at MIT looks at how we can cryptographically address this issue. And last year there was a presentation on how digital signatures can be used to protect query data, proving who actually inserted a row. A little later today after this talk, you'll get to see some work that we are doing on providing cryptographic verification of query results, making sure that the server didn't drop any results or add any. But in this talk today, we're going to specifically be focusing on what we've done to protect the confidentiality of data stored in Accumulo, using field level encryption and also some stuff we've done to protect access control. So at a very high level, one of the reasons we're giving this talk is that we want people to know about what we're doing so that they can begin using it in their own stuff. So our implementation of the work described here is nearing completion. And our hope is that it will be releasing to the community, everyone, sometime soon. And we've designed it such that it has drop-in compatibility with existing Accumulo code. So you change a couple classes here and there, but other than that, the rest of your actual code will stay the same. And with giving this talk, we hope that we can get feedback on the work that we've already done. And also when the code is released through open source, we'd love to have involvement from the community. So first, we're going to talk about what we've actually done to secure Accumulo. We'll then move on to, as all of you in the audience, how can you use it? And finally, we'll wrap up. So the first thing we wanted to look at when talking about securing Accumulo is that we have this problem that Accumulo administrator has the ability to read all of the data that is being stored in Accumulo. So an obvious solution to this is to just encrypt the data stored in Accumulo with keys that administrator does not have access to. This is going to prevent him from being able to read that data. And it's going to limit it so only the people that have the correct keys will be able to decrypt that data. So we can look at an Accumulo entry and see how it's broken up. We have a key and a value. The value is very likely to contain sensitive information if there's going to be any sensitive information at all. These are going to store things that are either personally identifying or maybe just mission critical that you don't want a cloud administrator to learn about your data. The key, though, can also have a lot of important information stored in it. For example, the row and column might also store sensitive information. And maybe it's not as specific as the data that is stored in the value, but it could still reveal things about your organization or about the particular data that you don't want revealed to the administrator. And then with the key, obviously, we have the visibility field, which is traditionally used to control access. So we use two different approaches to protect data. And to give you a point of reference, when we look at Accumulo as it exists today, besides those visibility expressions, it has no security guarantees against a malicious server administrator. But on the other hand, it is very fast. It is able to do a lot of tricks at the server side to reduce the amount of data that is actually returned to the client. So these query results can be returned very efficiently with minimal communication overhead and processing overhead. The two types of encryption that we will discuss today are what we call deterministic encryption and semantically secure encryption. So we'll start at the right side. So semantically secure encryption means that with a given key and a given piece of data, once that data has been encrypted, the adversary, or in this case the malicious server administrator, has no clue what that data was before encryption. So they learn nothing about that data. Well, this comes with a limitation on performance. It also means that that Accumulo instance in the cloud can do nothing to filter that data. It has no way of knowing if a given row would match a range. So all the data needs to be pulled down from Accumulo, and the client-side software actually has to do that filtering. So this is where we have maximum security, but with some performance limitations. So we also developed an approach that tries to be in the middle of these two, that is going to provide some level of security, but also some level of better performance at the query side. So this is deterministic encryption. What this means is, given the same key and the same data, the same ciphertext is always going to be produced. What this means, though, is an Accumulo administrator is going to see in his database, let's assume we had this is a really trivial example, but assume we had a value that was just storing male or female. Well, he's very easily going to be able to tell that there's a bunch of male values and female values, and he's going to know, he might not know which set of values is male and which set of values is female, but he's going to know all those rows refer to males because they're all going to encrypt to the same value, and another set of rows all refer to females as well. And if he knows some distribution about the data, maybe knows 60% of the data is going to be about males and 40% is about female, he actually can still learn some data. Because he can just look which rows have 40% of the data. Okay, well those are going to be female. Which percent has 60%? Those are male. Okay, he's learned the decryption. So that's where we have limited security. But in cases where there is a lot less well-known distribution of the data, we can still have some security guarantees against that Accumulo administrator. He's not going to be able to learn as much as he would like. But on the other hand, because those values don't change across different encryptions, it means we can search for them at the server. The client is able to encrypt those values and then say, search for this encrypted value, and then the Accumulo instance can search for that and return just those values to the user, who will then decrypt them. So obviously there's trade-offs between all these different approaches, between different levels of speed and different levels of security. So we feel that it's very important that that client software has the ability to configure what level of security and performance they need for specific tables and specific tasks. So for example, we might have a case where we have a sensitive row, a column, and a value. All three need to be encrypted. In this case, we're looking at medical data, so you have some patient along with a diagnosis, very sensitive potentially. And we might say, well, the patient name, as well as the fact that we're talking about a diagnosis, we will encrypt that deterministically so that we can look up diagnoses, or we can look up a specific patient very quickly without pulling down all the patients in the database. If that patient is indexed by an ID, that's going to be somewhat hard for a server administrator to figure out which encrypted texts refer to which patients. So we still have our security. But that value, specific diagnoses, might be very easy to link to a specific person. So we can use semantically secure encryption. decrypt that at client side to actually get the data out. So that kind of solves the problem of where we're only worried about an Accumulo administrator reading data that they shouldn't read. The other problem is we have this case where an Accumulo administrator might choose to give out data to users that shouldn't be able to get that data. So as an example of that, we have our Accumulo instance over here on the right. It has some data about a diagnosis that should only be available to a doctor, or if it's a nurse working in the ER, assuming that there's obviously some really big urgent thing, she can get that data as well. So in the correct use case, the doctor asks for a diagnosis, he gets the result. If a clerk at the hospital goes and asks for the data, he doesn't have those labels, and so he gets no results. Everything works as intended. But now if we switch out for a malicious cloud administrator that might be trying to collude with that same clerk, this time when that clerk asks for that patient diagnosis, he gets back the diagnosis data. The administrator is free to do this. As we've discussed, Accumulo does not prevent that administrator from tampering with those results when they get returned. So what we want to do is we want to figure out, what our approach was to cryptographically ensure that access control, according to visibility expressions, was appropriately enforced, so that only the clients that have those appropriate attributes will be able to access that data. So what we did is something we call cryptographically enforced attribute-based access control, or CEABAC for short, in case you hear me use that acronym. I might slip into it. So if we have this data up on top, which is the diagnosis, we're going to discuss how we insert it into Accumulo down here at the bottom. The first thing we're going to do is we're going to generate what we call the field key. This is just a completely random key. So obviously unguessable by the Accumulo administrator because it was just completely random. And we're going to encrypt the diagnosis data with that key. Well, now we need to make that key available to the people that will be decrypting it. And we want to do that in a way that is tied to the visibility expression. So the first thing we do is we break down that visibility expression. We see a nurse in ER or a doctor. Well, in the case and we're going to assign each of those attributes a key. So those are managed by some key infrastructure that we'll discuss a little later. But basically, every attribute has its own cryptographic key. Then what we're going to do is we're going to encrypt the field key using these different attribute keys. And we're going to do it in this manner. First, we look down and we see an OR expression. That means both sides of the OR expression need an encrypted copy of the key. So in the case of doctor, there's nothing below doctor, so we just take the key and we encrypt it with the doctor key, and we throw that into the table. On the other side, we look down and now we have an AND. That means they need both the nurse and the ER permission and that cryptographic key, so we split the key. And then we encrypt each of those splits with the appropriate key. That means that if a person later comes and they have the nurse and ER permissions, they'll decrypt both halves of those keys, re-put the key together, and then they'll be able to decrypt the field key, which lets them decrypt the data. So obviously, as you can see, there is additional storage here in the number of attributes and the complexity of the visibility field. So as I mentioned, this requires, though, that we have some level of key management for those attribute keys, as well as that field level encryption would need some way to retrieve those keys as well. And we also need to handle distribution, ensuring that only the correct individuals have access to the key. And then revocation. Users are going to lose rights. That's just part of how it works. They leave the company, get a different job. But we're going to need some way to revoke access to these keys. So when we look at the key management lifecycle we've chosen, the first step is that a user enters the system. So our key management server is going to need to generate keys for that user. It will then take those keys and encrypt them. It creates a kind of a package with all those keys, their attribute keys, and it's going to encrypt that package with the user's public key. And for the purpose of this, just assume we know the user's public key. It's kind of up to individual instantiations to choose how they want to manage users' public and private keys. In the third step, the client is going to query for their keys. They're going to get back that bundle of keys that has been encrypted with their public key from the key storage. They will then decrypt those keys locally and have access to their attribute keys. In the future, they're only going to need to re-talk to that key storage when keys have been revoked. Otherwise, they're going to be able to just keep using that same set of keys to work with Accumulo. And so in the case where a key is revoked, we are going to have to generate a new key for that attribute or that field, and then we're going to have to re-wrap that key, re-encrypt this new set of keys with the user's public key and put it into the key store. And that user down the road can ping the key store, say, are there new keys? If they learn they are, they can go up there and they can grab the new keys. So hopefully at this point you're all thinking, wow, that's amazing. I would really love to secure my databases. So the obvious question is, how do I go about using this software? So the most important artifact we've created in this regard is a Java library. It is currently targeting 1.8, though it would be really easy to backport it to 1.7. So there's 3 main classes to know about, I guess 4. The first is an encrypted batch writer. So the nice thing here, as I mentioned, this is just a drop-in replacement for a batch writer. So instead of calling connector.createBatchWriter, you call new encrypted batch writer, and you pass it the appropriate configuration that we'll talk about in just a sec. And then it works just like a batch writer. So the rest of your Accumulo code works as expected, except now you're writing encrypted entries into Accumulo using either field level encryption or that cryptographically enforced access-based access control, attribute-based access control. Similarly, we have an encrypted batch scanner, once again just a drop-in replacement for the encrypted, for a normal batch scanner. Because of encryption, entries might be out of order, so we fall, and that's what batch scanners guarantee, is that you'll get the entries, but they might not be in order. So we have the same contract. We also support server-side filtering of deterministic encryption, and we automatically will convert the given ranges so that they can be done on the server. And that involves there's actually a lot of logic that goes into what parts of the query and the range can be encrypted and sent to the server and what parts of the filtering have to be done on the client. But the library takes care of that all for you. So it's just like using Accumulo as you always have with ranges. And then the configuration is 2 new classes called an entry encryptor configuration and a field encryptor configuration. And when we ship this library, we already have multiple examples showing you how to set up these configurations. So it will come with documentation, it will come with examples, so you don't have to try to read our minds about how these configuration files worked. And they can also be loaded from INI files, as well as being configured programmatically. But at a high level, these configuration files allow you to say which fields should be encrypted and how they should be encrypted. So to show you an example of how easy this is to use, we have some code here as well as the configuration below. So in the code, we need some way to have an encryption key container. This is that key infrastructure, and we'll talk about what we've done to provide examples of that for the community in just a sec. So you instantiate that, you instantiate your batch writer config however you did normally before, and this time now you're going to create an encryption config from the INI file that's below, and I'll discuss that in just a sec. And then we call encrypted batch writer equals new encrypted batch writer. We give it the connection, the table we want to talk to, the batch writer config, and now the new parts are our encryption config as well as the keys needed for encryption. But then you can see it works just like a normal batch writer. You create a mutation, you add the mutation to the batch writer, and it writes it out to the server. So very much like what you're used to, you drop in this new class and it just works. We look at this configuration and you can see in general it's pretty simple. The different sections of the INI tell you what field we're discussing. So for example, where it says row, it means we're going to encrypt data into the row. We're going to use, in this case, a deterministic variant of CBC. We are going to use a key. The name of the key we're going to use to encrypt it is just called row key. Because this is field level encryption, we're going to use a 256-bit key, and it's going to encrypt data from the row into the row. Looking at the far right, we can look at the value. This time we're going to use GCM to give us some authenticated encryption, making sure that the data hasn't been changed after it's been written, giving us some authenticity in addition to the confidentiality. And it's going to be just encrypt value into value. And this time, because we don't give it a key ID, it knows to go and use that expression, the visibility expression, and use that with CEABAC to encrypt that field. So pretty easy. As we mentioned, we'll also give several example INIs when the source code drops so that you can all see how to do standard good configurations. So for the key infrastructure, there's a single class, which is the encryption key container. I misspelled it there. It's an interface that is any class that follows this interface can be used to host keys. What this means is you can either roll your own key setups or you can use one that we will be providing. We're going to provide a reference implementation that anybody can use to host their own keys, or they can use it to roll their own, using it as an example. And our system internally uses a separate instance of Accumulo to store these key wraps. So you do need to run it on a trusted system. So basically you might have your giant cloud system that hosts all your Accumulo data. That's all in the cloud. And then you'll have this smaller server that you just run locally that hosts key data for you, that you trust a little more than you trusted that big set of data that's out in the cloud and is harder to verify. So availability, right now we're in the process of finishing up implementation and getting this work open sourced. There is a Python prototype library that's a little farther along in the open source process, and the goal here is to show you what features will be available. In many ways, it's obsoleted by the Java library that follows it, but it's still, if you're especially itching to get to this, it's still going to give you a little taste of what we have. And our goal is sometime in 2017. Obviously, that's really vague. We are actively trying to work towards the first quarter of 2017. Sometimes things take longer than you expect initially, as we're all aware, but that's what we're really trying to get done. And as I mentioned, it will come with examples, including a reference key server that you can either choose to use yourself, use as a starting example for how to roll your own, whatever you want to do. So to wrap up, there are some limitations with the things we've talked about. We already talked about some with field level encryption, performance versus security. As we mentioned a little bit previously, you have to use deterministic encryption carefully. If you use it with data that has a well-known distribution, it can allow that Accumulo administrator to de-anonymize some of the data. This isn't really unique to our approach. It's unique with any approach that has searchable encryption. The male-female example is a great example of how you can de-anonymize some data. So it just needs to be used with care, but if thought through, it can be a very helpful feature. With CEABAC, there's some other limitations. Because CEABAC is completely random in how it encrypts the data, that means we can't filter it server side. Another one is that the user that encrypts the data and inserts it into Accumulo has to have all the proper attributes to be able to encrypt it. So you have to have these very powerful users that initially, you would need somebody, for example, in our example, that had both ER and nurse and doctor to insert that information. We are looking at ways that we might be able to get around this limitation, though. And CEABAC is it is susceptible to a collusion attack. So if we had somebody that had attribute A and attribute B, we had some expression that split that key and encrypted them with both. If you had Alice and Bob, who both had different attribute keys, decided to collude, they could each get part of the share and then combine that share and then decrypt those fields. There are ways to address this, but they all have incredibly bad performance, which is kind of at odds with how Accumulo works, which is all about having very high performance. So we are also investigating how we can make that better. Other things we're looking at is we're actively working to integrate this with the work that we've already done on signatures, as well as the work that you'll hear about after this talk about how to verify Accumulo results. Very important to us, so we're looking at ways that we can optimize our code, including increasing the speed of both field level encryption and CEABAC, reduce the storage overhead of CEABAC, and looking at how we can reduce storage overhead at the key server. So in every instance, we're just looking at ways we can make this faster and smaller amount of data that needs to be stored. We're also looking at how we might be able, so for future stuff, once this library drops, some things that we're still interested in doing are looking at how we could use cryptography to enforce different policies that are more complex than just who should be able to see the data. Things that could prevent attacks such as a phishing expedition from a malicious user who might want to just grab all the data in Accumulo to see what might be interesting and what he could leak or could sell to a competitor. We could look at policies that restrict the types of queries that users could run instead of just the data they could look at. That's something we're looking at. And also alternative methods for enforcing visibility expressions that have different trade-offs than CEABAC. So as we mentioned, we really would love to see participation from the community. We are working to open source this project, but once it's open sourced, we really would like to see the involvement from the community, helping us figure out how we can implement some of these new features, discussing what other types of security we would like to see cryptographically enforced, how we might optimize it, and then just having the community help us maintain it. As a research institution, there's limited resources we have towards maintenance, and so if we really want this to be a good library that continues to be usable years down the road, we would love to see the community helping maintain it. And another option is we'd be interested to see if there's potential for what we've done to be implemented more directly inside the Accumulo database itself, which might allow for more elegance and higher performance. So in conclusion, the work we've done is able to protect Accumulo against a malicious server administrator. And we really would like to start building community engagement. If you want to talk to us about if any of you are interested in this and want to talk to us, you can do it either at these sessions, or you can contact us at pace-contact@ll.mit.edu, and we will be sure to get back to you because we really are looking for this engagement. So I'll open up the time for questions now. Thank you.
Would you be providing any tool? Would you be providing any tools for what existing data into the storm, like read the current batch schedule or what it is?
So we haven't currently, but that's actually a great idea and wouldn't be something very difficult for us to provide. So looks like one of my team members is making a note of that, but that's something that we definitely should provide and would not be difficult. Do we have any other questions? What? Oh, sorry about that. The question was, are we going to provide any way that we can take existing stores of Accumulo data and encrypt them so that they can start being used with these new classes? Yeah.
Do you have any benchmarks for the performance implications versus?
Yeah, we did. They didn't quite make it into the slides. So there's definitely a hit in the performance, purely a large part because we are using encryption. So there are some limits. There's no way we're ever going to be as fast as Accumulo without encryption. To say it is somewhat slower, but we're actively working to continually lower that to kind of the bare minimum. So it's hard for me to say like how much slower, because it also depends on the ways it's being used. So it is a significant hit, but one of our real goals is to bring that down as much as possible. Oh, and the question, sorry about that. The question was, do we have benchmarks that show the performance hit? And with the open sourcing of it, we will probably be releasing those benchmarks so it's clear. It's not something we're trying to hide. It just didn't make it into the slides, and I'm a little newer, so I'm not the best person to discuss that. So you can find me after this, and my teammates might be able to answer it a little more accurately. Here, sorry, I couldn't really. So the question was, what is the impact on the increase in the storage side? So it really depends on which of the features you're using. So for example, field level encryption doesn't increase the storage size at all, whereas CEABAC has to store a little more data about those field level attribute keys. So that's linear. Basically, you have a new 128-bit to 256-bit block for each of the various keys that make up that attribute. So it's kind of tied to the number of attributes you have. And we are looking at ways to potentially further reduce that, though.
Have you done any scaling testing so we can see like how does it scale in terms of user interactions as well as size and scope of the system?
So the question was, have we done any scalability testing? And the answer is we're currently in the middle of that. We have another developer that's not me that is, his entire purpose is to write some really large tests that look about if we have just hundreds or thousands of clients using this, what is the implications of that, both in performance as well as stability? Okay, I think that's it. Thanks for your time.